Welcome back, students. Today we're going to look a little bit further in graph theory and we're going to look at an introductory problem. We're going to take a look at this map right here, which once a long time ago, a mathematician named Leonard Euler once looked at it himself. And by studying this map and by coming up with some um, realizations about this map, it really set the foundation for some of the topics that we have now in our current day graph theory. So this is a city over in Europe. If you want to read the names, you can. I'm not going to butcher them. But basically, what it is you have these bodies of waters that go through this city, and it's really cutting the city up into four sections of land. Now, to help us identify those four sections of land, I went ahead and labeled them as A, B, C, and D. And you can see that there are 7 bridges going across these bodies of water that are connecting these four pieces of land. And so, the problem that Euler was thinking about was, is it possible? Doesn't matter where you start and it doesn't matter where you end, but is it possible for a tourist to go through the entire city? So that means go to A, B, C, and D, not necessarily in that order, but is it possible for a tourist to go to all four pieces of land by crossing each bridge once and only once? So go ahead and I suggest that you pause this video and maybe take your finger and try to start off in different sections and try to cross each bridge exactly once and see if it is possible or not. Okay, so through trial and error, I think you're probably going to find that it is not possible. No matter where you start, it's not possible to cross each bridge once and only once. All right, so what we are going to do is we are now going to take this graph and we are going to turn it into another graph, but a more common type of graph that you're going to see in graph theory. And so here's what that's going to look like. Instead of actually drawing out each section of the land, okay, I'm going to use what are called vertices, or sometimes they're called nodes, to represent each portion of the land. All right, so each of my vertices, you can see they're just 4 dots because I had 4 sections of land. And then I named each of those vertices using just a capital letter. And that's what we do in graph theory is we have all of our different vertices. And then for each vertex that we have, we use a capital letter to denote the difference between each vertex. Now, it does not matter how I position them. I put them in order basically how my map appeared. So A, B, C, and then D off to the side. But if I wanted to, I could have made a rectangle out of this. Okay, A, B, C, and D, and these two graphs would be congruent because they still have the same vertices. They still have the same number of vertices. Okay, so it doesn't matter where you place your vertices. What matters is how many there are and how you name them. Next, what I'm going to do is to represent each of the bridges, each of the 7 bridges in the map. I'm going to create what is called an edge to connect them. So we have A going to B. There are 2 bridges. So I'm going to draw 2 edges going from A to B. Now, the graphs that we had last time, we had arrows on these because those were directed graphs. We went from one vertex to the next and we never backtracked in our projects. This time, we're free to go across the bridge and go right back. Okay, so there's no direction to these. Okay, so no arrows. However, what's important is there are 2 bridges, so I need to make sure that there are 2 edges connecting A and B. Likewise, I'll do the same with B and C. There are 2 bridges. And then B to D, there's one. A to D, there's one. And there's C to D, one as well. So I'm going to go ahead and draw those. Okay, so here are actually 2 possible graphs for what this map look like. Here it's more so where the vertices are in the same position as they were on the map. But what's important is we still have 4 vertices. So 1, 2, 3, 4 vertices. And then how many total edges? So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. How many going from A to B? 2, 2. How many going from C to D? Or B to C, there are 2 and 2 here, and then 1 from A to D, B to D, and C to D. Same here. So these 2 graphs, while they look a little bit different, these are congruent graphs because they still have the same vertices, the same number of edges, and the same edges connecting the same vertices.